Okay, complex conjugate and the division of complex numbers. Firstly, if we define z as a plus bi, we define the complex conjugate, which is z bar, as a minus bi. You may have done conjugate-like things with surds, so if you had a surd 5 plus root 2, conjugate, that'd be 5 minus root 2. We can show, if we multiply z and the conjugate together, something happens. So z times the conjugate of z is two complex numbers multiplied together, which we've recently learnt about, and we have this, and we have a squared minus abi plus abi minus bi all squared, because a squared, okay, the middle terms cancel, and we have, now we can step it out a little bit just so you can see. We have an I squared there, ding 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 ding, I squared alert, I squared is -1. Alright, that's every time that happens when dealing with complex numbers. Get ready to exploit that. So we have a squared, now that is minusing a negative now, so we've really got a squared plus b squared. So that's important. Take note. You might have heard the word modulus before. Now, modulus is related to the above result. Modulus is a little bit synonymous to the absolute value or the magnitude, and it's a synonym for that in other areas of mathematics. And you've seen that double bar notation before. The modulus of the given complex number above is the square root of a squared plus b squared. Familiar. You're thinking vectors. I've studied vectors. And it looks like Pythagoras' theorem. So that should, it should be familiar. It's make links to your other learning. Linking to other learning helps you remember things and understand them more deeply. Okay, now that segues into something else here. We're going to show some properties of the conjugate in our lead up to division. First of all, if we're given z1 is 2 minus 3i and complex number z2 is -1 plus 2i, show that the conjugate of the product of z1 and 2 equals conjugate z1 times conjugate z2. Okay, so let's try that out. So left hand side is, we've got to do the product first. So z1, z2, we need to look at that first, and that equals 2 minus 3i times -1 plus 2i. Okay, so going through all that, for z1 times z2 we get 4 plus 7i. Thus, we have the conjugate of that is 4 minus 7i. Okay, so now let's look at the right hand side. It should match what we've got there, and we've got to go, first thing we need to do when dealing with the right hand side is work out each complex number as a conjugate. So z1 conjugate is 2 plus 3i, and z2 conjugate is -1 minus 2i. Now we need to multiply those together. So therefore (2 plus 3i) -1 minus 2i time to multiply, and we've got -2 minus 4i minus 3i minus 6i squared. Ding ding ding. Alright, I squared alert. We have I squared is -1. We've got negative 2 minus 6 times negative 1, just rearranging the order, minus 4i minus 3i is minus 7i. Cool. Well, we've got negative 2 minus negative 6, and negative 2 plus 6 is 4 minus 7i. And looky there. Okay, right hand side concurs with the left hand side. QED. Now I want you to have your own QED moment. I want you to pause the video in a moment. Oh, that's not a good pause symbol. Hopefully yours looks better than that. Pause the video in a moment, but instructions first. We showed that I want you to show and put this in your notes and then show me next time you see me that Z1 plus Z2 conjugate equals, use the same complex numbers by the way. You could use your own, but yeah, show that because that's a thing as well. These are both important results. Okay, so that is an important result and I want you to convince yourself about that important results. Show the full working like I did with the multiplications. Okay, do it with addition. Show me. Okay, now for division of complex numbers, we have a few things to show first. Okay, well, if we have something like this, 1 over a plus bi, which is 1 over, it's like saying 1 over some complex number z1. Okay, it's a bit like saying that. And we multiply it by the conjugate of the denominator, which would be a minus bi, and multiply top and bottom so that we're actually multiplying by 1. We get something. We get a minus bi over a squared plus b squared. You might need to show some extra steps, but look, you should know the algebraic identity anyway, that x plus y, x minus y is x squared minus y squared, and you might say, but that's a plus sign you've just written. But remember, when you square the I part, it's negative 1, so that changes it minus to a plus. Okay, so we've got that, and so if we have a plus bi, the standard Z1 complex number, which is actually the reciprocal of what's written there, and we multiply it by 1, which doesn't change anything, the reciprocal of 1 is 1, we have a squared plus b squared over a minus bi, which of course is the reciprocal of that. So basically a plus bi, if we change that now, times this, that will equal 1. Because basically you're multiplying by that. You're multiplying a plus bi by this, because this equals that. And then if you take the reciprocal of that, it is the multiplicative identity, I should say. And so if we can rearrange that, we get the multiplicative, we get the identity. So these must be inverses or multiplicative inverses of each other. Alright, so these are multiplicative inverses. So to formalize that, we have Z inverse, which is the multiplicative inverse, is equal to a minus bi over a squared plus b squared. Z conjugate over the magnitude of z. So make sure we note that. So the multiplicative inverse of a plus bi is a minus bi over a squared plus b squared. I've just realized I've written something upside down up there. When I changed that to a multiplication sign, I needed to flip that over. Let me fix that up. There we go. So that previous line, sorry, corrected. I've got to reciprocate that second fraction there. So a minus bi over a squared plus b squared, which matches what we've got here. So basically the multiplicative inverse is the conjugate over the modulus squared. So when we divide complex numbers, if we've got z1 divided by z2 here, that's the same as z1 times the multiplicative inverse of z2, and using our result from up there, that's the same as z1 times the conjugate of z2 over the modulus squared of z2. Now, of course, this is provided we're not using the zero complex number for z2. That would screw everything up. I'm going to end the video with an example of division of complex numbers, and given that we have z1 and z2 as such, find z1 divided by z2. So what we do is we write down the given information and operation, and what we do is multiply by the complex conjugate of the denominator of z2, top and bottom. Multiply numerators together, so we have 6 minus 4i minus 3i plus 2i squared. Ding ding ding, I squared alert. Alright, can you still read that? No, that's awful. Okay, that's better. So over a plus ba minus b is 3 squared minus 2i squared, or all squared really. And I'm using that difference of 2 squared identity that I showed just before, or you could do it the long way, suit yourself. And we've got on the numerator the 6 and the 2 times, now I squared is negative 1, so it's actually negative 2, so 6 take 2 is 4, and 4 minus 7i over, now I squared alert there too, because that is 4 times I squared there. Alright, so that 4 times I squared is 4 times negative 1, which is actually negative 4, and so we have 9 minus negative 4, we have 9 plus 4, which is 13 there. Oh, I've made a mess. Let me fix that up. Alright, so 13, 13, 13. The aristocrats will want to do this, and that's fine by me.